Okay, off we go, and here's where we were last time. We were talking about change of variables. We kind of didn't really quite even get to the actual change of variables formula, but we covered the segue, which is to take this particular point of view on the substitution rule. And you all remember substitutions from way back, right? And again, you can think of it as a technique or something, but really I think it's better to think of it as an equation. This is a true theorem. Certain conditions being satisfied. So the big takeaways, the big point of view that I want y'all to, in particular, think about here is, for one thing, we're talking about a pullback in the sense that if the function goes one way, then expressions go backwards. They go the other way. This is just intrinsic to the process of plugging stuff in. That just is what it is. Right? So things go kind of backwards. Important point to keep in mind. The other thing to keep in mind is that a little piece of the domain, when it goes through the function, will turn into a different sized little subinterval, specifically having been stretched by a factor that uncreatively I'm going to call the stretching factor, right? And that has to be inserted as well so that we can make sense out of dx in terms of dt. All right, so those are the big ideas, and as we discussed last time, what we're going to do here now in the multivariable setting is just try to kind of rip off those ideas. Same thing. Different details, of course. We'll have to figure out how those details work, but big picture, it's the same idea. If we have a function going one way, we would hope and expect that an expression, such as an integral, would go the other way. Namely, it would pull back. Notice this means, just like it did for substitutions, that whatever the domain is for the integral that you're going to sort of start with on the right-hand side, right, that needs to be the image of some other domain on the left. Or, said differently, when you do the pullback, right, the domain is going to pull back too. And so the new, you might call it, domain over here will be the preimage. Like so. Okay. All right, so yeah, plugging stuff in is still just plugging stuff in. If you literally have a function that goes to the right like this, that means x and y are literally functions of u and v. You just plug those in. And then the only remaining point is to think about the stretching factor, and specifically how much bigger, if you take this little piece of the UV plane, when you plug it into the function, it will turn into a different sized, presumably, piece of the target over there. And by what factor has that been stretched, right? If I want to be able to claim that area in the XY plane relates to area in the UV plane, well, they're not equal. The XY area is going to be different by way of some factor, and again, calling it the stretching factor. Okay, so I think we talked about all this stuff last time. What we do need to work out, at least claim, is what is that stretching factor, right? And now I in previous years have gone through at this stage of the presentation and actually proved the formula for the stretching factor. And the thing is, there's already a lot going on with this. We need to see, I think it's very helpful to see some examples first. So I'm not going to prove this formula yet, but I will walk through the broad brushstrokes of the argument in a bit. For the moment, I'm just going to assert that the stretching factor is this formula. It's the absolute value of the determinant of the derivative matrix. Quick reminder, the derivative matrix is sometimes called Jacobian, right? And as such, this determinant on the inside of the absolute values is regularly called the Jacobian determinant. And you're going to hear me say that a lot because I grew up saying that. Okay. All right. Now, of course, y'all know what the derivative matrix is. It's the matrix of various partials. Make sure to get them in the right order. It's easy to accidentally transpose. Surprisingly easy. So do be careful about that. And then one other little point of notation, outside of the absolute values, just looking at the determinant. Very convenient, as it turns out, to rewrite that like this. And I'm going to give you a couple of motivations for this notation. On the one hand, if you look at the matrix, the partials of x and y, okay, well, they're numerator of this fraction-looking expression, partial x and y. And notice that the partials of x and y are being taken here with respect to u and v. And so thus these are the bottom half of that notation. So kind of suggestive, right? That's kind of nice. The other thing that I like about this notation is that with that in mind, if you look at what we have on the left here, and I'm going to use that notation, I'm going to rewrite this stretching factor here as partial xy, partial uv. Don't forget your absolute values, of course. Right, and then we have du dv. And the suggestion is that gives us area over here in the xy plane, and so this I'm going to rewrite as dx dy. And altogether then, look what we have. We have the suggestion that this is equal to that, and it's almost as if those cancel. Now, they don't. There's not an actual cancellation here. Long list of reasons, right? Not the least of which, this is not a fraction, right? This is notation that we made up for highly questionable reasons, as being vaguely suggestive of what we're actually looking at, right? So this is not a cancellation, right? But golly, it sure is convenient that it almost kind of looks like it is. Right? And so when notations are convenient, that kind of does make them desirable, even if there's danger. Right? This again, the suggestion that this is a fraction is sketchy. All right, how we doing? Everybody with me? Okay. So again, to the question of why the stretching factor is what I'm claiming it is. We will talk about that later. For the moment, I want to get a win under our belts. Right? So we're going to look at an actual example. Here we go. We are going to start with the unit square over here in the UV plane. Right? We're going to imagine that there is a function called g here. And we are going to imagine, and then what happens if I take my unit square, if I plug it into that g function, right? And what comes out, the image of what comes out is what we're going to call d. That's the set over here in the xy plane. Ends up looking something kind of like that. And that is going to be the domain for my new integral that I want to compute, right? So that's the question at hand, right? Is to compute a certain integral over this domain on the right. And let's take a quick moment to recognize what an annoying question this would be if we had to come at this sort of brute force, right? If this was our domain and, we start slicing up and then, of course, we hit this corner. And then we keep slicing, blah, 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 and then we hit this corner. And then we have to keep going. Oh, whoops. We have to keep going to finish it up. So we would have to turn this into 3 separate integrals. Nobody wants to do that. That's clearly a bummer. Worse than that, arguably, is the fact that we don't know the equations of these curves, right? Arguably, I might be able to make the case that I could kind of I can come up with a sort of a parameterization of that curve right there, because I have x and y as functions of u and v, and I could argue that that's what you get when you go across this edge right here where v is constant. So loosely speaking, I could parameterize this as a function of u. But again, that's a parameterization. It's not an equation. So we would have some algebraic challenge in front of us to actually even find what the equation of that curve is. So that's a really hard problem if you don't use the trick that we're about to use. Let's see here, pausing real quick. I want to re-highlight my thing here. Is everybody on board so far? Okay. Now, reminder, our brand new tool here. If we're going to do this pullback, right? If we're going to take the given integral on the right-hand side, and if we're going to turn that into an integral on the left-hand side, I need a couple of things. I'm going to need to know what this stretching factor is. The stretching factor is going to involve taking partials of this g. This g, therefore, will have to be known. So I'm going to need to know, my domain is the image of something by way of what function? I am also going to need to know what my new domain is, my pullback domain. I'm going to need to know what domain over here in the UV plane is it whose image gives me that domain that I started with. And that is what is very convenient about this as a starter example, is that those things are given. Right? We are straight up given that my domain is the image by way of this function of this unit square. So in some sense, everything that I need for the pullback is given in the statement of the question. Well, I guess I have to take some partials, but a lot of the setup is given. We good so far? All right, so we just need to compute the stretching factor. Stretching factor involves taking the partials with respect to u, and then the partials, of course, the next with respect to v, right? As indicated down here, u partials followed by v partials. A little bit of differentiation makes sure you're good with partial derivatives, like so. You take the determinant. Therefore, we have our Jacobian determinant. Keeping in mind, though, very importantly, our stretching factor is the absolute value of our Jacobian determinant. So we're going to have to take the absolute value of 4uv minus 9. And how in the world am I supposed to know? Is this positive or negative? Could be positive, but I see a minus 9 there. 9's a pretty big number. Maybe this is negative. Hard to tell at a quick glance. Right? So the way we resolve this is by keeping mind of what for which values of u and v am I going to be interested in this expression. I don't need to worry about what this expression's doing with values of u and v that have nothing to do with my question. And u and v, here they are. U and v range over my new domain. These are the only values of u and v I care about. And I can see right there from the domain that u is always between 0 and 1. Right? So that u right there, always between 0 and 1. Likewise, this v right here, also always between 0 and 1. So keeping in mind, what the domain is, what that tells me about what u and v are doing, I can now revisit this expression and point out, okay, well, this first term is never bigger than 4. And that means that the thing inside of the absolute values is never more than minus 5, which means it's always negative, and the absolute value of something that's always negative is the negative of itself. Everybody buy it? Okay, yeah.
What if, for example, the domain for u and v was from 0 to 2?
Yeah, then we'd have a problem on our hands. Yeah. Well, what we'd have to do is subdivide the domain into two regions. One where this expression is always negative, go like this, and then I'd have to, on the other side of the line, I'd have to have a different formula for my Jacobian determinant. A different formula for the absolute value. It would be just 4uv minus 9, and I'd therefore have two separate integrals. Yeah, which would make this not a very good first example, because I want this to work out awesome. and that wouldn't be that. All right, how's that? Is that cool? Is everybody happy? All right. So yeah, we have our stretching factor. We'll go ahead and stick in our stretching factor just because otherwise I'm a little concerned I'd forget it. It's an easy thing to forget, so you might consider that. Otherwise, everything else in this question is really just a matter of plugging in. What are we going to do, for example, with this x right here? How do I rewrite x in terms of u and v? Well, our function up here tells me x is literally that function of u and v. And so that is what goes there. It just replaces x. Is that cool? And you can see right here, x is the first output of our g function, and thus the just algebraically look at that first output of the g function. And then, of course, analogously, y being the second output from my g function, y is right there, and thus goes right there. What do you think? Everybody all right with that? Okay, now, was this a good choice? Was this a win, or did we just successfully make the problem harder? And at a quick glance, you might be tempted to say, hey, this made things a lot harder. After all, my integrand used to be just linear terms. It's a nice integrand, right? Whereas now my integrand is quartic. So maybe this was a bad idea. Maybe this is better. We should just take what we had in the first place. But no, because look at the domains. The domains are really the problem, right? The first integral, however nice the integrand is, sure, but the domain is a nightmare, fraught with corners and lack of equations. Right? That's a really hard domain to work with. It's 3 separate hard integrals, right? Whereas our new domain is everybody's favorite domain for a double integral. 0 to 1, 0 to 1, nothing to it. Super easy. Everybody happy? All right, so big win. Doesn't look like it at a quick glance, but it's a big win. Okay, now reasonable question comes up. How do I, in general, know what function I should use as my change of variables function? Will it always be given, such as in this example? And sad to say, no, it will not always be given. It's not how the real world works, and therefore not how this course works. So there are different tricks, strategies that you can use to come up with change of variables functions. Mostly it's a matter of having seen examples, sort of analogous examples, and then note to self, hey, if I find myself in this particular scenario, here's a tool that would work nicely. Right, so I'm going to approach this from a tools in your toolbox point of view. Here are some change of variables functions that are useful sometimes. You can translate points. Shifting things around can make things more convenient sometimes. Just be aware that what your change of variables function does to points and what your change of variables function does to domains is, again, kind of backwards, right? So if you look back up here, so if our function goes that way, right, then the domain that I am sort of starting with is going to turn into the domain that is over here on the left. It's going the opposite direction. And so you're going to find there's sort of an oppositeness in what this does to your domains. If you translate in one direction, the domain is going to pull back, exactly the opposite. Stretches turn into squishes. Counterclockwise rotations turn into clockwise rotations when you're doing the pullback. And I'm going to show you an explicit example here now. Now you'll notice with this example, again, the question is to compute an integral. Again, the domain is given. This time, though, it's not given as being an image. There is no given pullback domain, and there is no given change of variables function. So it's going to be our job to try to figure this out. You know, what change of variables function should I use? Okay. First thing I'm going to point out is this is what our domain looks like. I'm going to leave the geometry of this as an exercise for you all to think through. Persuade yourself, and please do be careful and precise about this, that these 4 points define this square. So you can think about this from a vector algebra point of view, you know, pairwise subtract, persuade yourself these two vectors are the same, and these two vectors are the same, and that this is a right angle. You can use a dot product for that. Think it through. Okay. All right. Okay, so that said, what should be my change of variables function? Let me ask that question to myself in another way. What nicer shape could I start with, and then what would I have to do to that nicer shape to make it look like this? And I think a reasonable proposal is that we view this square as having been counterclockwise rotated to produce the blue square. There's different ways you can think about this, but that's the approach I want to take here. Does everybody see that? Counterclockwise rotation of this sort of, highly desirable squared off square. Counterclockwise rotation of orange produces blue. Okay, so assuming we're good with that, notice that what that means then, when I do the pullback, I will, having been given this square, my new pullback domain is effectively the result of sort of turning it to the right to give me the orange square. All right, so when I go backwards through that linear transformation to produce this orange square, which you might whoopsie, here we go. You might sort of imagine that as sitting over here like that. Not that of course it's not. It's not in the XY plane. It's in the UV plane. But you can see it's sort of going the opposite direction. Everybody okay? All right. Okay, so now some details. First of all, how do we do a rotation? I'm going to mostly remind you that this is Math219. Rotations are linear transformations. Linear transformations are written with matrices. Matrices have the feature that the columns are the images of the standard basis vectors, and blah, blah, blah. Think about the geometry of how this rotation would, what those images would be, and you get this as your rotation matrix. That's a lot of little details. Make sure you're good with it. If you're not, if you're a little shaky perhaps on the linear algebra, or maybe the geometry that goes into finding those column vectors, come to my office hours, please. I'll be very happy to walk you through it. You, of course, have other options, other resources, friends, classmates. Office hours have the other instructors. You've got several options, but please do make sure that you're good to go with that. And then you can look at your specific square here and note that angle is pi over 6. And therefore, this matrix becomes specifically that matrix of values. Everybody good? Okay. All right. So we have ourselves a change of variables function. X and y are functions of u and v. You got to multiply that out, but still. Okay, that noted. The derivative matrix is just this. That's just partial derivatives. Again, make sure that you can do that. Right? Double check, make sure you get the right answer. The stretching factor is the determinant of that matrix, which is easily confirmed to be 1. I view this as being a kind of an eyebrow raiser that, wait a second, there was trig and fractions and square roots, and the stretching factor was exactly 1. That seems a little weird. Until you remind yourself, of course, the transformation we're talking about is just a rotation, right? And when you rotate, things don't get bigger. Rotating is a rigid motion. Sizes don't change. You would expect, just geometrically, you should kind of expect that should be 1. Does that make sense to everybody? Okay. Now, that's for your own sort of personal sort of double-check purposes. On an exam, you do have to show me the calculation. If we have an exam question about change of variables, one of my intentions, I hope clearly an obvious intention, is that you demonstrate proficiency with the big ideas, namely how to compute a stretching factor. So on an exam, even if it's geometrically obvious, do make sure to show the calculation that will be required and part of the grading system. Okay, but yeah, nice to know what the answer is, right? So you're going down the right path. Okay, it's basically all over at this point. We put the absolute value of the Jacobian determinant right there. Again, I know my formulas for x and y. This x right there, I can see is that dot product, which then goes right here. Right, and likewise, y, this y right here, where does that y come from? Here it is. It's the second coordinate, so it's this dot product, which goes right there. And again, a little bit of algebra, move things around, and we get a nice, simple final answer here. And again, this is a big win. Even though the integrand is a little weirder, I've got some weirder constants in here as opposed to nice round integer constants here. This domain had corners all over it. My new unrotated, you might say, pulled back domain. Nice constant bounds, no corners to worry about. Much more desirable. Yeah. Did you have a... No? Okay, sorry. Yeah, okay. No worries. Okay. Yes?
Why in this one are we using the determinant?
One more time, say.
Why in this one are we using the determinant? We're using the derivative to replace x and y. Whereas in the last one we just used the function that you gave.
Oh, no, we're not using... No, so x and y, like x is this formula right here, and that's just explicitly from the formula itself. Is that cool? Yeah. Yeah, you may be kind of pointing at, now there is another sort of weird fact here, that the matrix representing the linear transformation and the matrix representing the derivative of the transformation, they are the same matrix, and that's a little unexpected, right? We'll talk more about that later today. But in fact, that does hold as a general fact. Yeah. Okay, anybody else? Everybody all right? Okay, a couple of little formalities that have to get said. These aren't going to really be an issue to speak of in this class, but in order for these ideas to work, your function does have to be continuously differentiable. There's problems with definitions of things. Things get a little out of hand if we don't have that. Again, not going to be an issue for us. And they do also have to be invertible. The problem is that if your function's not invertible, then you can't make this case let's see, oh gosh, come on, move, there we go. Then you can't claim, as we have done in general here, that when you push forward to see the image, and then you pull, and then you pull back to get the pre-image, if the function's not invertible, that won't work out as conveniently and nicely as we were sort of assuming it would. So invertibility is another particularly important thing. And again, it shouldn't be an issue for us in this class. Okay, all right, moving along. Sometimes, as it turns out, our functions go in the wrong way. So we need a method to help us deal with the scenario of the function going the wrong way. So let's consider a function going the wrong way and think about how we would compute what the stretching factor is. And there's a really nice little punchline. Starting with the arrow going to the right. So thinking of x and y as functions of u and v. We have a formula for our stretching factor. Notice it's always the partials of the output variables with respect to the input variables. That's how you compute a stretching factor for a change of variables function. Partials of the outputs with respect to the inputs. And that's our formula. Okay, fine. Well, now what if the function was going the other way? What if u and v are functions of x and y? Well, there's nothing magic about right versus left. It's just inputs and outputs. And so, same general idea. U and v now are the outputs whose partials we take with respect to the now inputs x and y. So this little expression here is the stretching factor of the sort of backwards change of variables function. Okay, now you're going to be tempted to look at these and say, these two things here, these are obviously reciprocals of each other. Right? The numerator became the denominator became the numerator. It's this business here, and that's how fractions work. Right? Seems very tempting to say that very clearly, of course, these should be reciprocals of each other, except that, wait, no, not at all obvious, because these aren't fractions. This is notation. This was a very presumptuous notational choice where we said, there's a context where these things kind of sort of vaguely sort of behave kind of like fractions, and so we just choose to write them as fractions, even though they're not fractions. These are determinants, right? You look back at the definition of these things. Oh, come on, why won't this thing? There we go. You look back at the definition. Here it is. Right? The definition of this sort of vaguely fractional-looking thing is that it is a determinant. It's not a fraction. So do be careful about this, please. I mean, there are a lot of situations where we have little handy, little convenient notations that make it look like something is something that it isn't. And there's a pretty good case to be made that this is sloppy and dangerous and abusive, and we really shouldn't do this. But we do. It's very common. So what we find ourselves needing to know then is, all right, what is the relationship between these two things and why? And the good news is it works out great. Here's the argument. Imagine we have some set over here, whatever that might be. Right? And I could imagine what would happen if I plug in to that function. Well, I get some new set. Some new set like this, whatever that is. And now we could ask, okay, well then what happens when I take that back the other direction? Well, keeping in mind that these functions have to be invertible to even call them change of variables functions. If I take the orange set and go over and then back, the result is exactly the same orange set. So altogether, how much has area been stretched by going over and then back? Not at all. Right? The area has been stretched by a factor of 1. And so you can just straight up write that down. The stretching factor going forward is that. The stretching factor on the way back is this. And grand total, we've gone from the orange set to the orange set, and area has not been stretched at all. Therefore, that product is 1. And therefore, these are reciprocals of each other. Just like they kind of look like they ought to be with this nonsensical argument about fractions, right? So, very importantly, this result is not true because these things are fractions. They aren't. This notation that makes them look like fractions is reasonable because this is true. Right? The implication goes the other way there. Everybody buy it? Okay, we're going to make use of that in the following example. The following example does require a little bit of setup, so I'm going to have to talk for a bit here about exactly what's going on with this example. So here we go. We have 4 curves, and those 4 curves are as I have drawn here, vaguely, kind of, something like that. And what's bounded by those 4 curves is this region in here. And I want to recognize that this looks like a highly manufactured, artificial, unrealistic, implausible sort of scenario, doesn't it? And it's not. This is actually very, very real world. Those of you who are engineers will eventually take a class in thermodynamics. And in thermodynamics, you'll study something called the Carnot cycle. And the Carnot cycle, roughly speaking, involves a picture that looks shockingly similar to this. The numbers are a little weirder. I've cleaned that up to kind of streamline the process, but morally, it looks a lot like this right here. So this example that we're doing is very natural in terms of applications to physics. So how do we deal with this? As with a lot of our examples, you can look at this set here and think about how you would slice this up. But tragically, you can see this coming. We have a corner there and a corner there. And so as I slice, I hit that corner and I have to start a new integral until I hit that corner, at which point I have to finish with yet a third integral, right? So this is super annoying. As if I were to come straight at this, just start slicing things up in the usual way, this is a brutal, triple effort situation, right? Okay, so what are we going to do about this? The following is a delicate but powerful trick. I did not think of this. I was pretty intimidated by this when I saw it for the first time. I thought to myself, I would have thought of that on my own, right? So do keep in mind, that's not where the bar is. You don't have to have thought of this on your own. You have to be able to kind of mimic it after having seen someone else do it, right? And I learned this lesson by mimicking my math teacher way back when, and y'all are going to do the same. So the trick is this. Step 1 is to make sure that your equations are written as level sets. Whoops, let me get back into the right mode here. Make sure they're written as level sets. Notice that these are written as level sets. If your equations are not written as level sets, rewrite them as level sets. That's going to be important. You'll see why in a second. Okay, Next, pair them up like this. You'll notice we have two curves that are level sets of xy. We have another two curves that are level sets of xy squared. And I'm going to take the first function here, xy, and I'm going to call that u. And I'm going to take the second function here, xy squared, and I'm going to call that v. Neat trick. Again, I wish I'd thought of it. Right? This is how the process is going to work out nicely. View your curves as level sets. Use that to identify two functions you'll call u and v. And then notice between the two of them, that tells you how to view u and v as functions of x and y, and you have yourself a change of variables function. Now, it's going the wrong way, right? If we wanted to pull back, I mean, this is what we have, this is what we want, we need to go that way, we're not going the right way. So it's algebraically backwards and not clear what we're going to do about that. But nevertheless, change of variables function. Here's where it gets beautiful. Let's think about one of these curves, such as that one right there, xy equals 1. What does its image look like over here in the UV plane? Well, xy is u. So that curve that was xy equals 1 is now just u equals 1. That's a straight line in the UV plane. That's what's slick about this move, right? And you can see now why it's important that these equations got viewed as level sets, because I need constant here on the right so that I will have variable equals constant over here on the left, which is what makes them nice straight up and down, horizontal, vertical, straight lines. Is that cool? Real slick move. Okay. So, it's a great little tool for your toolbox. All right, and likewise for the others, and you can persuade yourself then pretty easily that the domain over here in the UV plane that corresponds is just this nice little rectangle. Okay, so let's compute our stretching factor. Let's see here. We have u and v as our outputs. We're going to take the partials with respect to x and y. Those are our inputs. There's our Jacobian determinant. Multiply it out. And we have that our Jacobian determinant is this expression right here, xy squared. And now we have to ask ourselves, wait a minute, is that what I need? Is that the correct stretching factor? Is that backward? I'm a little concerned it might be backwards because our function's going the wrong way. Maybe I'm squishing when I should be stretching, or something like that, right? The easy way to keep track of this, again, is with the notation. We started off with a dx dy integral. I want to rewrite the dx dy in terms of du dv because I want this to turn into an integral in the UV plane. So I need to know what's the relationship between dx dy and du dv. And this sketchy, but very handy notation here will keep track of that for me. And so I ask, what would I multiply by du dv to get dx dy? And, well, you can see right here, that partial xy, partial uv is what I need, because after all, I need, oh gosh, forgive me, but it's as if those cancel. Again, they don't. This is a horrible crime, right? But this is a horrible crime that will always point you in the right direction. And so it's a very nice little memory trick. It's a way to keep yourself straightened out. Is that cool? Okay, so we realize then that that's what we need. I need partial xy, partial uv. I have partial uv, partial xy, because that was easy to compute, because I knew formulas for u and v. I don't have formulas for x and y. I have formulas for u and v. So this Jacobian determinant I can compute. I need, however, the reciprocal. And so this thing that we actually need, I argue, is the reciprocal of the thing we actually have. What do you think? Everybody good? Okay. All right. There's one last bit. I mean, we do have a UV integral now. We've already celebrated the fact that our domain in the UV plane is just a rectangle. That means it has constant bounds, nice, easy constant bounds like that. It's all looking pretty good, except there's this one annoying, unfortunate reality is that I do still have my integrand is still in terms of x's and y's. And that's because as it was initially set up and to this moment, I still haven't solved for x and y. Now, I could, right? Y'all are good at algebra. You could look at this and get clever and figure out how to write, x and y as functions of u and v. But the whole point of this example is we don't want to have to rely on that. Sometimes that's not even feasible algebraically. The fact that it is here is just a coincidence that I'm going to try to ignore so that we can focus on, more importantly, the method. So how am I going to rewrite this expression in terms of x and y, in terms of u's and v's, without knowing x and y specifically? And there is, I'm sad to say, no pat algorithm for this. There is a strategy that works, often. And of course, any example that I give you, there has to be a reasonable way to solve the problem, right? So I'm not going to put y'all in any scenario where I haven't given you reasonable tools for answering the question. But here's the basic idea. If you want to figure out how to rewrite an expression of x and y in terms of u and v, the short version is guess, and then fix it. Right. So here we go. I'm going to guess and then fix it. Here's my guess. I have a product of powers of x and y. I want to write that in terms of u, which is a product of powers of x and y, and v, which is a product of powers of x and y. Now, just thinking out loud here, what would I do to products of powers of x and y to produce a different product of powers of x and y? And I propose that a reasonable guess would be to take a product of powers of my given products of powers, because I do know that will produce at least some sort of a product of powers, and I can hope to fiddle with those numbers a and b to get the needed product of powers. Now, this is a guess. I do not know, as I write this down for the first time, that this is going to work. But you see how it's a reasonable guess, right? If you have a product of powers and you want to write it in terms of product of powers, you're pretty sure cotangent's not the tool, right? Why would it be? It just doesn't make any sense, right? This seems like a plausible guess. And then when you multiply this out, it just works. Very much as you might expect. You multiply that out. The x exponents have to equal the y exponents have to equal. You can then solve and get your a and your b, and thus the expression that we were interested in the first place I've got it now written in terms of U and V. So, like I say, guess, right? Educated guess based on the forms that you're looking at, and then work out the specifics. Okay. All right, this is a pretty good stopping point, and I guess we're out of time, so it doesn't really matter anyway, but we'll draw the line right there. See y'all later. Have a good one. See you on Wednesday. Don't forget about attendance if you came in after I started.